Booklet 3 of the Secretary Suite consolidates a coherent, constraint-governed vision for next-generation computational architecture centered on hybrid photonic CMOS systems operating under the Swigert theory of everything AO. Unlike speculative treatments that prioritize raw performance or abstract supremacy claims, this booklet is concerned with how computation remains correct, stable, and governable as physical substrates evolve. The 4 papers collected here document a progression from architectural foundations through material realization into formal restraint and finally to instrumentation provenance. Together, they establish that any meaningful advance in computational capability, particularly those exploiting interference, phase encoding, or analog convergence, must be bounded by explicit physical, algorithmic, and governance constraints in order to remain scientifically credible and operationally safe. This booklet does not present a monolithic processor design nor claim experimental validation of new physics. Instead, it defines a durable evaluation framework, a way to reason about hybrid photonic acceleration without conflating performance gains with altered logic, authority drift, or untraceable physical assumptions. Computation is treated not as a black box amplification of intelligence, but as a settlement process governed by equilibrium, measurement discipline, and constraint enforcement. By anchoring advanced optimization architectures to name physical instruments, measurable coherence bounds, and explicitly stated restraint classes, Booklet 3 serves as the CPU-level backbone of the Secretary Suite. It ensures that future accelerators, photonic, analog, hybrid, or otherwise, can be assessed, compared, and evolved without compromising correctness, stability, or institutional trust. This paper proposes a hybrid compute chip architecture designed to achieve quantum-like computational behavior at room temperature without relying on fragile cryogenic qubits. The core hypothesis is that computation can be reframed as an equilibrium-driven stabilization process in a measured, phase-encoded physical substrate. The proposed chip combines conventional silicon transistor logic for deterministic control with an on-chip metamaterial photonic lattice composed of dense photon gate arrays. Each photon gate is treated as a measured boundary condition with 3-point sensing, pre-gate, mid-gate, and post-gate field measurement. These measurements are used to enforce symmetry-like constraints and to guide the photonic field towards stable solution states. The architecture is expressed in the language of the Swigert theory of everything AO, emphasizing encoded equilibrium, constraint-governed stabilization, and attenuation as structure as a functional computational resource rather than loss. The result is a credible engineering pathway toward high parallelism, interference-driven computation under normal operating conditions, with explicit constraints, validation tests, and failure modes. The photonic layer is explicitly positioned as an optional accelerator. All correctness, authority, and decision integrity remain invariant whether or not the photonic substrate is present. This paper presents a hybrid compute architecture that reframes computation as equilibrium-driven stabilization within a measured photonic substrate. Conventional silicon logic remains the authoritative backbone, while a metamaterial photonic lattice provides optional AO-aligned acceleration through interference-based settlement. The defining innovation is the photon gate as a measured boundary condition with 3-point sensing, enabling symmetry-like enforcement and structured attenuation as a computational resource. This architecture offers a practical, testable pathway to quantum-like advantages at room temperature without altering correctness, authority, or governance, and without dependence on fragile qubit systems.